I am David, your developer on duty, and in this video we talk about the downside of the Rust programming language. Rust is a very popular programming language, and according to Stack Overflow surveys, it's the most loved one since 2016 up until today. It gets a lot of hype, and projects heavily advertise that they are written in Rust because the resulting binaries are usually blazingly fast and correct with respect to a variety of error categories. So let's first talk about the good parts. Rust is fast and efficient like C, but it feels more high level. Correctness is guaranteed through the compiler for a variety of error categories like use after free or race conditions. It comes with a novel concept of ownership and borrowing, which eliminates the need for a garbage collector or a manual memory management. It comes with modern features like an expressive type system, pattern matching, or macros. But there are also some features which are both good and bad. For example, it comes with guardrails for your architecture, meaning not everything you design can be achieved in safe Rust because of the ownership and borrowing rules. But very often this results in cleaner architectures. It's also very explicit. That means when reading code, you will be able to see some details which remain hidden in other programming languages, but at the same time, you might be overwhelmed with visual clutter. This will be the topic of the following examples. Let's start with an example in JavaScript. Let's say we have a class employee, which has a constructor, which sets the internal name to whatever comes in the constructor and has a method called greet, which just prints the sentence, hello, my name is this name. Now you may have functions which may or may not return some employee. For example, const get employee option equals to math random, and if it's smaller than .5, then I create a new employee called David. Otherwise, I return undefined. Now, usually when you call this function, then you sometimes assume that you get a valid employee, which is not always the case. So for example, if you then call the greet function on this returned object, you might get a runtime exception. And here you are. So there's no guarantee that the code runs without runtime exceptions. Therefore, you need to have a great discipline, especially when you're working in a team. So let's fix it. It can also happen that there are errors. For example, wrong credentials. And now when we call it, we have no way to tell that this function will or can throw an error without looking at the function. Let's do the same in Rust. So we create our employee struct, which has a name, and it has a function greet, which takes a reference to self and prints, hi, my name is. Let's add the rand crate. Now we can create the function to optionally return an employee. Get employee option. It returns an option of employee. So if random, and we want a bool, if this is true, then we return some employee with name David, and else we return none. Now let's call this function. Now if we would try to access the greet method, it would be not correct. And the compiler tells us. And therefore we have to correct our code. And now it's working. And there will be no runtime exceptions. In a similar way, we can also return some errors instead of an option. So let's first define our error as an enum, employee error, and it can have wrong credentials. And we can also derive debug. Now instead of having this employee option, we have get employee result, which will return a result of employee or employee error. So instead of sum, we return OK. And in case of an error, we return employee error, wrong credentials. In order for us to call it in our main function, we need to change the signature a bit, because now the errors might bubble up, and therefore we return a result of an empty tuple and an employee error. If everything is fine, we return an empty tuple, and in the meantime we can get our employee result equals to get employee result. And now if we try to call the greet method on employee result, we will get an error by the compiler. Therefore, we need to use the question mark operator, which would bubble up the errors. Now we can run it, and you can see it works. And the big advantage is that in our code, we can now see where the error can occur. It cannot occur here. It can only occur here where those question marks are. So if you compare the Rust version to the JavaScript version, you'll see that it's a bit noisier, but at every stage it's clear what happens. The code is more robust and, in my opinion, a lot easier to read and understand, because you don't need to guess what the functions are doing. You know what they're doing because of the expressive type system. But this is just a tiny program and doesn't really reflect the complexity of real-world software projects. There we have, for example, asynchronous programming and complicated ways to satisfy the borrow checker, which makes writing programs a lot harder and not straightforward at all. With all the Rust hype, this fact is often neglected and can easily scare off many new Rust programmers. Let's dive in and have a look. So again, let's first start with the JavaScript version of our example scenario. We will create a web server which has a route returning hello world. And in addition to that, we create a logger middleware which can enhance the functionality of this handler to also log start and end at the beginning or end of the request. As a web framework, we're going to use Fastify as an example. So npm install Fastify. We can require it and call it. Now we can say Fastify get and register a route on the root endpoint with some handler function which we're going to define in a second. And we can listen on port 3000. Now for this handler function, it's an async function taking a request object, and we just return hello world as an object. Now we want to enhance this handler function with a logger which will log start and end at the beginning and end of this handler execution. So we can just write const logger equals to, it takes an inner object and returns a function which is a function which is asynchronous and takes a request object. We can log start and end, and in the middle we can call this inner function with the original request object and return the response. Now to enable it, we just write logger of handler. Now let's run and test it. And you can see it works. Now let's do a similar thing in Rust. And we need a few dependencies: tower, Tokyo, hyper, and futures. So let's implement it. First, we need to make the main function asynchronous. For this, we need an event loop for which we use Tokyo. Now we need to have a socket address. And we create the address. We use 127.0.0.1 and port 3000. Now let's create our server. For this we use hyper server as well as service make service function. And we can write let server equals to server bind, and we can provide the address. Now let's also register some service, so we can say let make service equals to make service function, and it will take a connection which we're not going to use, and we have here this async implementation, and we can just say that let our service be hello world, which will be a struct which we define in a second. And we can just return OK with infallible. And that we can give our server make service. And in the end, we run server.await. Now, infallible needs to be imported. Use standard convert infallible. And now we have to define our hello world service. Now this service is a tower service, so we can import it, tower service. And from hyper we not only need the server but also body request response. Now we can create our hello world struct. So this shall be our service. So we implement service of request body for our hello world struct. And we can implement the missing members. That's a nice feature of the language server. And now we have to specify the types. So the response will be a response of body. The error will be infallible because it cannot fail. And the future will be a ready of result self response self error. Now we have to import ready, which we get from the futures crate. We also need standard task poll, because now we can implement poll ready. So poll ready is a function which handles back pressure. So the service, if it knows that it cannot handle any more requests, it can just say, I'm not ready. So here we can just say poll ready with OK, because we are always ready. Now the only thing left to do is to implement this call function here. So we can also say we are ready we respond with OK and create our response. So it is just some hello world string. And now this should work. So let's try it out. Cargo run. It's running. And if we send an HTTP request, we receive hello world. Now for our hello world middleware, it's not necessary to create an own struct and implement the tower service trait for our struct to have this middleware. We could have also used the service functionality and only create an async function returning the hello world body. But we also want to create our logger middleware later. And for this, we need to implement the service trait. So it's a good way to see how the service trait works. Unfortunately, Rust does not have async traits yet. That's why we need to have here this future type, which is kind of a mix of our response and our error and yields some future. And this call function then returns this future. Now let's create our logging service. So it's also a struct. And this logging service shall have some inner service of type S, whatever S is. And we implement some new constructor which takes an inner service and returns self. And our inner will be our inner. Now let's implement the service trait for our logging service. Now we have S and B. And we implement the missing members. Now our response is the response of the inner service, because we just want to do some additional logging. So this is S response. The error is also the error of the inner service. And the future will be, let's say, the future of our inner service. Later on, this will turn out to be not correct. Now, of course, we need some trait bounds. So we say that S shall be service of request of something B. Now our service is ready when the inner service is ready. So poll ready is nothing else than self inner poll ready. And we provide the original context. And for our call function, we can print start. Then we can call the inner service with our request object. But now it gets a bit tricky because we want to return the result of this. But we want to print end after the execution of this inner function has been awaited. And we cannot just run await here because this is not an asynchronous function. So what we need to do is to create a new future where we await the inner service call, and that's something we need to return. And it turns out this is futures future box future of static result self response and self error. And now we can do the following. We can say box pin async move, and this is something which we're going to return. And since this is async, we can call await, and after we called it, we can print end. But you can see that there are still some errors. So now it gets tricky again to fix those errors. So we need more trait bounds. So this service here, this S needs to be static, needs to be clone and needs to be send. Then B needs to be static and send, and S future needs to be static and send. And what we can now do is we can say let mute inner equals to self inner clone, and then we use this cloned service. So now that our compiler isn't complaining anymore, finally we can use our logging service. So we can write logging new of our hello world service, but the trait bound clone is not yet satisfied for our hello world struct. So we can derive it. And now hopefully everything should work. So let's run cargo run and send some HTTP request. And you can see start and end is successfully logged. Now there's a slightly better way by using the map function of a future. For this I can use futures prelude. Now I can use the map function, so I can do the following. Instead of doing this, I can just say self inner call with a rec object. I take the result and map it. And here I can just say print end and return the result. Now the problem is that now this future type doesn't correspond to the return of this call function anymore, and I have to adjust the future type here. And now the resulting future type is futures future map as future, and now I can provide a function pointer, function result self response and self error, and this function will return result of self response and self error. And now it should work. So let's try it. Cargo run. And you can see it works. Now the biggest downside of this approach is that I use here a function pointer, and the function pointer here doesn't allow me to capture the environment. So if, for example, I would want to print some information of the request object, I wouldn't be able to do it because I cannot capture the environment here inside this callback function. And if I would need to change fn to impl_fn, then this would also not work. So the final solution, which I'm not going to implement here because it's a bit complicated and tricky, and which is also the solution for the official logger middleware of Tower, is that you return in your call method a so-called response future, which you define yourself. So your future type is now a response future type. And after you call it, you store the result in this inner attribute here, and also the context if you wish. And for this response future, you need to implement the future trait. And the future trait has this poll function here. And you can basically match on self_inner.poll. And once it's okay ready, then you can basically log end, if you will. And you also have access to this context here. So you can see it's quite complicated with many different types, and absolutely not straightforward to come up with that solution. So if you compare the Rust implementation with the one in JavaScript, you can clearly see that there's a huge difference. In JavaScript, you can read the whole implementation in less than a minute, while the Rust one has a lot of complicated code, mostly because of futures and the absence of async traits. Fortunately, the Rust team is working hard to support this. That will then drastically reduce the amount of code you have to write. Until then, there's also the possibility to use the async trait macro, which would also simplify the process. This example of this tower service is taken from a video by David Pedersen, who created a detailed walkthrough of this service, and please watch it if you want to know more details. My conclusion is that there are many benefits in Rust's explicitness. It leads to clearer and more robust code, see my first example, but in real-life scenarios you will encounter situations where the hard requirements of Rust's borrow checker will make your life a lot harder. After all, Rust is a systems programming language and will require more work upfront compared to high-level languages like JavaScript. I hope you enjoyed this video. If you have any opinions or questions, please post them in the comment section. Thanks for watching and stay tuned.